base, and it turned it sort of a green. And you'll see that cabbage juice goes anywhere from a bluish green to a green. And if you have a super strong base, you can get even this yellow. So we've got a wide range. So now that we've tested thoroughly with several acids and several bases, do you think that cabbage juice is an indicator? Yes, so we got some pink colors for acids, purple is neutral, greens and bluish things, and yellows for the spectrum of bases and concentrations. So, if you're asked, how can you figure out if something's an indicator, don't just say, see if it turns one color in a base and one color in an acid, because that could just be an accident. You have to test several bases, several acids, and see if all the acids turn this color and all the bases turn this color. Okay? So that's a definite key point that you want to follow. Now, of course, we've all seen that I really don't like pH paper. Litmus paper, not awesome. So I ran out last year, but what I'm going to do is take these coffee filters and just poke them down in here and soak them with cabbage juice, and then they'll become a really great pH paper that I can use. So they'll turn pink with an acid and green or blue with a base, and then we'll have kind of more informative pH paper than just the red and blue. I'm going to stick it down here so hopefully I don't spill it. Let's see, where are we now? So indicators, good. Pretty good. Okay, let's look at some review questions and practice problems, and then if we have time, did you all read about the dilution equation this week?
I did.
Okay, so only if you're going to be absent all week and had to get ahead. But we'll talk about the dilution equation a little bit to get you kind of a head start, and so I have time to show you some extra things. I know one other thing. This is a salt. I'm not entirely sure if it might be magnesium sulfate and it might be sodium chloride. I don't really know which one it is because nobody labeled the bag. Ooh, it's leaking too. That's lovely. So what do you think the pH of the salt will be? If I put some salt in here, do you think the pH will change? Can I get it to leak out? Yes, it can. Right out of the bag.
Use the leak.
It's better than spilling it everywhere. Alright, so we've got a little bit of salt, and I know it's a standard salt, either magnesium sulfate or sodium chloride. So do we see any color change?
Very slight. Like the very first thing.
Okay, so we're still pretty much a neutral pH color. What do you think would happen if I mixed an acid and a base?
And it would get closer to purple.
Okay, so we're heading closer to purple, we think, so. Alright, that was like super basic because I put a ton of sodium hydroxide in there. So we're still really far from acidic. Very basic. If I put all the acid in, well, there's still like undissolved sodium hydroxide in there, so we may never get this to be anything but super basic, and I probably should be careful how I dispose of that. I'm going to rinse one of these out too and test out every year. I have to do this because the indicator we're going to use for our lab next week when we do a titration lab is phenolphthalein. And there are a few details that are a little different, but phenolphthalein changes from colorless to pink at a certain pH. I want to say that pH is a little bit above 7. So a pH above 7 would be acidic or basic? Basic. So if it changes color when it's basic, I think I have to put it in the acid. But I always have to test it because I can never remember for sure. So I rinsed out this test tube, and I'm going to put a little bit of the acid here, just vinegar in it. So next week's titration will be, alright, so I'm going to put 2 drops. You guys will probably use about 2 drops next week. Okay, it's colorless in the acid, so that's good news. So you'll put your acid in a little flask next week, like, not a beaker, but a tiny Erlenmeyer flask. You'll have a burette, which is like a large one of these, with a little nozzle at the end that you can go drip by drip by drip, tiny bit by tiny bit. And so you'll drip in the base into the acid. Now, you guys remember we had trouble with the balloon lab, and part of the cause of error that we hypothesized about was that perhaps the vinegar, since it was 5%, isn't exactly the concentration that we thought it was, right? So we're going to titrate vinegar to find out exactly what concentration it is. And so you'll drip your base right into here, and I don't want to contaminate that. So, like if I take, for example, well, that base is contaminated. What do I have over here? I have some sodium hydroxide in here. So let's say I try to titrate this without spilling it. Just real quick. And you can see what you'll see next week. So I put a drip of base into the acid, and I go drip, drip, drip. Sodium hydroxide is cheap, and I can always make more, so I might end up using a lot of it. So we go drip by drip by drip. And right when you lose patience and start squirting too much, now this is the warning for next week. And I tend to lose patience way too fast with the titration. You want to go slower than this once you start seeing the barest hint of pink. So I'm going to stir. We want to make sure, sometimes you have a density difference, especially with concentrated acid, which you won't next week, but you might for the final. I'm going to run out now. Okay, so now I'm starting to barely see a little bit of pink. Can you see it? If I come close, can you see like the tiniest hint of pink? Tiniest hint of pink. Tiniest hint of pink. It'll start to linger. See how it lingered? When you get to the I'm lingering point, that's when you want to be really careful. Because what you want to end up with next week is the very palest pink you can get that stays for 10 seconds. And that's when you know you're at the end point of your titration. So that's kind of a heads up for what you'll read next week, just because I want you to be able to kind of understand it better. So somebody remind me to make a new solution of sodium hydroxide before I need it again. But that, like I said, is an easy thing to do. I was going to make ammonium hydroxide with you guys today, and I still will if I can get the time.
What did you bring a really strong acid for?
What?
What did you bring really strong?
This is actually a really strong base. It's the
base.
ammonium hydroxide. And I would like to, I'm out of ammonium hydroxide solution because I did something like that with it and used it all. And so I need to make more for a lab we'll do in the future. Now I need to make more sodium hydroxide. But I always make a bunch of that for the final, so I always can get a good supply of that. The ammonium hydroxide is more stressful to make, and we can use a dilution equation to make it because it's a liquid, and the sodium hydroxide is that powder. So, let's start with Maddie. Review question 1. State whether the substance described as an acid or base. Probably tastes bitter.
Base.
Feels slippery.
Base.
Turns blue litmus red.
Acid.
Yes. And Brittany. Okay, so here's something I didn't tell you guys that we want to make sure we talk about. So Brittany's problem says identify the acid in the following reaction. And it gives us this. pH3 plus C, this thing. So, did you get to do your homework? I know you were gone.
I did my, I did review questions.
Okay, so if we have this reaction right here, it wants you to identify the acid. So what do you think?
I picked CH4 because I'm assuming you can go to the hydrogen and then turn into the CH3. Yeah.
Exactly right. So you saw that a hydrogen disappeared from it, and clearly it donated one of these 4 hydrogens. And because you know that something that donates a hydrogen is an acid, you pick that one, that's perfect. So if that's the acid, this is the base.
Yeah.
And here's a key point. One of the things that just never occurred to me to tell people before I taught chemistry, if they say identify the acid in a reaction or identify the base in a reaction, it's going to be one of the two reactants or three reactants if you have three reactants. Don't pick a product. You're going to get it wrong if you pick a product. Pick a reactant, okay? Also, if you get stuck, look at what you can see and think about what you know. You guys know NH3 is a base, ammonia. You work with NH3 frequently. pH3, if you think about periodic properties, nitrogen and phosphorus have very similar periodic properties. NH3 is a base. pH3 is probably a base. It's going to behave just like ammonia, because if you think even about their Lewis structures, right? I mean, they're exactly the same. And when something will donate a proton to it, that new proton that gets donated to it just moves right in here, right? To share some of this unshared pair. And then you end up with a plus charge developing because they just got a whole proton but no electron. So you can see that their chemistry is just identical. So you'll start to recognize things based on things you already know. And, of course, since we have two covalent, an acid that's covalent and a base that's covalent, we make two ions. So just things to observe when you look at these problems. Lily, some books define base as a proton acceptor. Why is this just this correction as the definition that was presented in the book?
Because donating an H plus ion is basically the same thing as donating the proton.
Good.
So accepting one is the same.
Right. So if the book says a base is a hydrogen ion acceptor, hydrogen ion is a proton. So obviously, and that question was hard for a lot of people because they couldn't figure out what it was even asking. But it's just trying to get you to say that a proton and an H plus ion is exactly the same thing. So Saul, which ones of these are polyprotic acids?
Oh, B, C, and D.
Okay, so B and D are polyprotic acids.
I actually had a question about you. Does that work the same way? You said like when you have water, it'll always be H and OH.
Well, no. If you look at A, we'll look at A and C because B and D are the right answers. So why is A wrong?
Because it only has one.
Okay, so this is nitric acid, only has one H, so it's a monoprotic acid, not a polyprotic acid. But it is an acid. Okay, it's just got one proton, so it's not polyprotic. But this, calcium hydroxide, why is it not a polyprotic acid? Can it donate a proton? No, it's a base. Hydroxide is like, if you have a compound with a hydroxide in it, it's a base. So this is a base. Hydroxide is like, I'm a base. So if you don't have a proton that can be donated, it's a base. Well, and especially if you have a hydroxide, it's a base. I mean, not necessarily. If you don't have a proton to be donated, it's not necessarily a base. It might be a salt or something completely different. But if you have a hydroxide, it's a base. What is that milk with magnesium? It's probably magnesium hydroxide. And it's a base. Hydroxide means base. And Jolene. So we've got, which of the following units could be concentration units? So we haven't talked about concentration much yet. Sorry.
Yeah, we only had 4.
Oh, okay. Oh, you didn't do that? Ah, okay. So let me tell you a little bit about concentration for next week, just to make sure that you remember thoroughly. All right, so we talked about moles like 2 months ago, 3 months ago, right? And you remember that you can find the molar mass of something using the periodic table, right? So let's say Well, let's look at this, for example. This is ammonium hydroxide, so how would I write the chemical formula for ammonium hydroxide? What's ammonium?
So it'd be NH4OH.
Okay, so we have an NH4 plus ammonium and OH minus hydroxide. And you just switch the charges and you get ammonium hydroxide, just like Micah said. So if I wanted to find the molar mass of ammonium hydroxide, what would I do?
Just add all the acids.
Add them up. Nitrogen's 14. Okay. So 14 plus 5 hydrogens would be 5.05. This is one of those few times hydrogen makes a difference. And oxygen is 16. So we get, what, 35.05. Since these guys are all to the 10th place on your periodic table, you have to round to the 10th place, but the 5 actually does make it round up. So we're going to find the molar mass of this to be 35.1. And what units do we use for molar mass? So AMU would be 1 molecule
But
of
for the
ammonium
molar mass, we would
hydroxide.
say grams, right?
Okay, so 35.1 grams is in 1
For every mole.
mole of ammonium hydroxide. Okay, so here's our molar mass of ammonium hydroxide, just as a quick review. You guys will have to do a lot of that this week. If you get grams, you're going to have to convert to moles, so don't forget, it's not like metric where you can just move the decimal point and go from grams to moles. You have to find it on the periodic table, and I've seen that happen before. Don't do that. So find your molar mass there, and then if it were powder, I could measure out 1 mole by measuring at 35.1 grams, dilute it to whatever solution I want, all set, easy. So concentration is, well, let's say, if I'm looking at the concentration of this, it doesn't actually say on the bottle, but I happen to know, it is 15.0 molar. This capital M here, if you have a capital M, what it actually means is moles per liter. That's the worst L ever. Moles per liter. So what this means is there's 15.0 moles of ammonium hydroxide in every 1 liter of solution. All right, so if I had 1 liter of this, I'd have 15 moles of ammonium hydroxide dissolved in it. Clearly I don't have a liter, I have 30 milliliters, right? So I could figure out how many moles are in here by saying, well, I have 30 milliliters. How many liters is that? 30 mils, 1, 2, 3. And if I type that into my calculator, 15 divided by 1 times 0.03, I would get anybody, I don't know it.
0.450.
Really?
All the right numbers.
You can keep,
3 significant.
I can keep 3 because 300 would be 3, and this really is 3.0, there's 3 there. So 0.450 moles, almost half a mole of ammonium hydroxide in this tiny bottle. It's a lot of molecules of ammonium hydroxide. So, well, I might as well finish it now that we've started. And now that we're done review questions, I didn't realize they'd be fast. We need to do practice problems, but we're doing okay time-wise, I think. So, all right, we just talked about ammonium hydroxide. I want to make a solution of it. Now, here's stuff you haven't seen until next week. But when you have a very concentrated solution, or even, I mean, this is like a really concentrated solution, and you want to dilute it to be a solution you want to work with, because nobody wants to work with 15 molar base. That's not, I mean, like 1 drip of it would, yeah, it's like the yellow thing that keeps being yellow even when I pour all the acid in. It's just so concentrated. So, molarity is concentration times volume of the concentrated stuff. Solution, I guess I could write. is gonna be equal to the molarity times the volume of the diluted stuff you're making. This equation is called the dilution equation, M1V1 equals M2V2, and it's just a quick way to figure out how to make a solution. So let's say I need to refill my little bottle here. That's sodium hydroxide, that would be bad to refill. This is ammonium hydroxide, and it's supposed to contain a 0.10 molar solution. So let's write a problem up here. Black marker maybe. I'll write it like Dr. Weil does. A chemist needs, well, and here's another limiting factor. The only piece of glassware I have, I need 30 milliliters of it. But the only way I can make the solution is with this adorable 50 milliliter volumetric flask. So I have to make 50 milliliters of the solution. And volumetric flasks, how many significant figures will it give me? It'll give me out to the hundreds, please. Oh, and I need to. Yeah, that's not perfect. Hot NaOH there. Okay. So I need to make 50.00 milliliters of 0.1 molar ammonium hydroxide. So I can refill my little bottle with the right stuff that goes on the label, right? She has Alright, so if I have 15 molar ammonium hydroxide and I want to make 0.1 molar ammonium hydroxide, how can I do it if the piece of glassware I have makes 50 milliliters of my new solution? So, what you do is you make sure you keep the concentrated stuff on one side of the equation and the dilute stuff on the other side of the equation.